Computers have become important tools for geologists to handle data storage and retrieval and to compute many kinds of measurements. There are many focuses in the realm of geology. Some geologists study minerals and mineral composition. Others study the way Earth moves and the way its plates interact with each other. And still others look at the way different materials act when they encounter each other. Computers and computer simulation play an important part in all these facets. In geology, special computers operate instruments for analyzing rock samples, others plot maps, and some help determine the most promising locations for mineral deposits. Geologists use computers and software as tools in the areas of geological problem solving, report writing, and presentations. A variety of Windows-based software applications including word processing, HTML editors, spreadsheets and graphing, image manipulation, drawing, presentation and ArcGIS are most used by geologists nowadays. In this chapter, we will look into following aspects, including fundamentals of computers and how computers help geologists, utility of computers in geological studies, applications of computer in geology, the future of information systems in the earth sciences. Computer fundamentals. Computer is an advanced electronic device that takes raw data as input from the user and processes these data under the control of set of instructions called program, and gives the result, that is output, and saves output for the future use. Functionalities of a computer. Any digital computer carries out 5 functions in gross terms, including takes data as input, stores the data, that is instructions, in its memory and can use them when required, process the data and convert it into useful information, output the information, control all the above 4 steps. Computer hardware. Hardware represents the physical and tangible components of the computer, that is the components that can be seen and touched. Examples of hardware are the following, that is input devices including keyboard, mouse, etc., output devices, that is printer, monitor, etc., secondary storage devices, that is hard disks, CDs, DVDs, etc., internal components including central processing unit or CPU, motherboard, random access memory or RAM, etc. Coming to the computer software. Computer software is a set of programs which is designed to perform a well-defined function. A program is a sequence of instructions written to solve a particular problem. There are 2 types of software, including system software and application software. The type of software geologists use depends on their focus. Some may use program focused specifically on map analysis and representation. One program may focus on maps that show fault lines, another may give a view of mineral deposits layers. Some programs compare multiple kinds of information in one map. Other geologists use 3-dimensional or 3D programs to test the strain on the rocks in specific shapes. Some use simple diagnostic programs that show the geometric qualities of minerals and maps. Some of the popular software used are ArcInfo, ArcGIS, Elvis, MapInfo, AutoCAD, GCD Kits, Rockware, Rockworks, IGPET, Petrograph, Surfer, Aquacam, StatPack, TiliaPast, etc. Utility of computer in geological studies includes mathematical concepts as well as computers can be used in almost all stages of problem solving. At present, the greatest shortcomings are the availability of the archival data and the elaboration of methodology in applying mathematical models to the construction of time-space geological models. The geologists dealing with the application of mathematical methods, therefore, are concentrating their efforts on these two problems. Application of computer techniques can be divided into two groups. Number one, techniques of data processing for forming geological data banks as well as for automatic calculations. And number two, the techniques related to mathematical modeling of geological phenomena by statistical, deterministic and stochastic process models. Computers in geology. There are many focuses in the realm of geology. Computers and the computer simulation play an important part in all these facets. Some of the usage are in mineralogy. Some geologists work to study specifically how minerals respond to stress. They use engineering programs to simulate different stresses based on the information about different types of stone that they have collected. These programs are used to test sites for various building projects or examine mineral-based construction materials for integrity and suitability. Coming to the modeling, when many geologists study natural disasters that are affected by the earth, such as earthquakes and volcanoes, using very intricate computer programs, they create models of these disasters to better understand how they work and how certain events set chains of action into motion. Computers are then used to sense and even attempt predictions of these events. Information sharing, geologists travel from place to place, testing soil samples and giving their opinion on the rock formations nearby to help others make decisions. To help, they use portable computer devices to analyze the soil or compare topography maps to their surroundings. Time management is including the computers and computer programs that geologists use has drastically cut down on the amount of time geologists need to do their survey work. A project that once took days or weeks now only takes a few minutes with the right software. This has changed the time priorities of geologists drastically. Instead of asking other geologists for help and comparisons or collecting materials, geologists can now use computer programs to immediately compare findings around the world. Many companies are hiring fewer geologists now that so much can be done by only one. Computers in geological photo interpretation, computer processing now seems to be essential in geological photo interpretation. The procedures developed to date comprise estimation of operator resolution, digitization of annotations to arrays of cells, fitting perception models and using the model parameters to assign probability estimates to quality maps written as shade prints or on film writers. Computer processing of digital remote sensing data can produce imagery of high spectral and geometric fidelity without the degradation associated with the photographic reproduction. This is a significant advance in quantity or quality control in the data acquisition system. Number two, the use of computers in petroleum exploration. A computer exploration or computational advances in the area of petroleum resource assessment allows modeling of economic potential for large areas. These techniques include both economic and geological considerations. Programs and techniques for computer mapping have improved significantly during the decade. Contour mapping now is probably the most important application of computers to geological aspects of petroleum exploration. Data banks have grown tremendously, and rapid interactive retrieval systems permit display of combined seismic and geological information as maps and cross-sections. Many computer systems are promising to bring dramatic changes to log interpretations, procedures, and to the making of subsurface lithofacies map, increasingly valuable exploration tools for defining stratigraphic traps. Data banking, log analysis, and contour mapping are extremely basic procedures routinely required for almost all exploration activities. Aside from the more exciting geophysical applications, the use of computers in petroleum exploration seems to have advanced during the past decade through the determined refinement of such basic techniques. And number 3, use of computers in seismic reflection prospecting. Computer determination of parameters such as instantaneous frequency and instantaneous phase carried out by complex analysis of waveforms may provide information on lithology and hydrocarbon content not obtainable from conventional processing. Important progress has been made in computer modeling of seismic data. This involves ray path modeling for precise structure interpretation and stratigraphic modeling to relate waveforms and amplitudes to subsurface layering. With the introduction of three-dimensional recording, modeling techniques have been determined particularly useful in the interpretation of the data thus obtained. The digital computer has brought about revolutionary improvements in our capability to study geology by the seismic reflection method. New recording and processing technology has brought us much closer to our ultimate goals of extracting the same geological information that would be retrievable if there were a borehole to the maximum depth of interest at every shot point. These improvements in the seismic art have made it possible to map structural features with more accuracy and to present them more correctly. They also have enhanced our ability to identify lithology and deduce stratigraphic relationships from reflection data. Perhaps the most spectacular development of the past decade in seismic exploration has been the capability under proper conditions of detecting gas deposits on seismic record sections. Making a use of the fact that reflections from the top of gas-filled sands have higher amplitude than those from water or oil-filled sands, digital recording and processing makes it possible to preserve relative reflection amplitudes on seismic records. This could not be done with analog techniques because of their limited dynamic range. Geological structures can be mapped with more precision by automatic techniques for transferring reflections from their apparent positions based on reflection times alone to their true position in space. Wave equation and frequency domain methods are employed for such migration. Three-dimensional recording and processing procedures greatly increase the accuracy with which complex structures, particularly in areas of tectonic disturbances, can be mapped. New capabilities made possible by digital processing now allow the geophysicists to derive lithological and stratigraphic information of a type that was not obtainable previously from seismic reflection records. Filtering programs are available for extracting from complex source signals simple symmetrical wavelets that enhance resolutions of reflections and allow better discrimination of stratigraphic relations. True amplitude registration facilities determination of reflectivities at lithological boundaries that permit constructions of synthetic velocity logs. Presentation of such logs for all shot points in record section form allows mapping of velocity, which with proper well ties can be converted into a lithological cross section. comparable to that which would be obtained from closely spaced boreholes. Such presentations give valuable information on stratigraphy in areas where conditions are favorable. Number 4. Computer applications in petrology. One of the most interesting uses of computers in geological work deals with the seismic exploration for oil. Small man-made earthquakes are produced by compressed air, a small explosion in a drill hole, or by a special vibrating truck. Echoes or reflections of energy from underground layers of rocks are detected and recorded on magnetic tape. These data can then be transmitted via satellite to a data processing center. Computations of times required for thousands of these echoes to occur are interpreted by a computer to locate areas where deep rock structures may contain oil or gas. The computer applications in petrology have been concerned with databases, petrological mixing models, and the use of multivariate statistical techniques, and more recently the modeling of the igneous differentiation trends. Recent developments in petrologic mixing models include a better understanding of the principles behind various models, in particular the fact that for constant sum major element data, a constraint model should be used. A completely generalized model capable of dealing with metamorphic reactions on the type A plus B plus C equals to D plus E plus F plus G also has been developed. The use of principal component analysis or PCA factor and discriminant analysis in the interpretation of the chemistry of igneous rocks and mineral groups has become increasingly popular, but unfortunately, either through the ignorance or the use of statistical packages, some of the interpretations have been incorrect. In particular, a principal component analysis or PCA based on the correlation matrix seems difficult to justify for major element geochemical data. Number 5. Computer applications in exploration and mining geology. The manipulation by computer of large databases has made possible a closer relationship between geology and mine system analysis, and between geology and mining. Although many applications of computers to exploration and mining geology have been developed, their use and acceptance in mining was limited, even by the technologically advanced countries. Today, most mining companies and governmental agencies concerned with natural resource apply computers extensively. Classical statistics for mining geology has been refined further as the result of many detailed applications with much feedback from industrial practice. The contribution and statistics and computers to geological exploration for mineral deposits is significant, although the most extensive applications are in the mining of known ore deposits. Particularly influential have been: number 1, the development of models for drill hole exploration, and number 2, operations research methods to conceptualize and organize exploration effort. A significant step has been the development of many computer programs, some relatively large and complex, for the computer analysis of data from the mineral industry. Exploration, geochemistry and geophysics grew at an explosive rate. Today, many computer applications have been made for the organization, display and interpretation of these data. Coming to number 6, computer as a research tool in paleontology. In many areas of paleontological research, the computer has taken its place with the microscope and hand lens as a basic research tool. Most of the standard applications are digital and include various types of biometrical analysis, information processing including collection management, computer graphics and statistical testing of hypotheses. Paleontology, especially evolutionary paleontology, is undergoing a major transformation from a primarily ideographic science devoted to building a chronology of the history of life to a more nomothetic science in search of general statistical laws. The computer may not be responsible for this shift of emphasis, but it may be the vital catalyst. In the nomothetic approach, species are treated as particles and the group behavior of large number of species or evolutionary events is best treated by the computer. This is true for two reasons. Number one, testing models with real data requires massive data processing capability, and number two, Monte Carlo and numerical simulations may be necessary in the formulation and testing of theoretical models. Along with the search for general statistical laws in the evolution of life, there is a new emphasis on the complex Markov processes, and any history, and particularly evolutionary history, contains Markovian elements. Whether the computer analysis is done analytically or by simulation, it is important to be able to treat Markov series, especially time series and branching processes, in a massive and rigorous fashion. For this, the computer is indispensable. Number 7. The computer in paleoecology. Access to the electronic computers is necessary for modern quantitative paleoecology, as almost all problems are highly multivariate. Diversity studies are becoming increasingly abundant in computer-based paleoecology. Multivariate statistical applications are the most important area of computerized paleoecology, involving both standard multivariate elements as well as special adaptations. A useful concept in paleoecological reconstructions based on borehole data is the ecologue, a union of physical and biological values. Coming to the 8th point, that is computer in geological field mapping. Digital geological mapping is the process by which geological features are observed, analyzed and recorded in the field and displayed in real time on a computer or personal digital assistant, that is PDA. The primary function of this emerging technology is to produce especially referenced geological maps that can be utilized and updated while conducting fieldwork. Computer technology and software are becoming portable and powerful enough to take on some of the more mundane tasks a geologist must perform in the field, such as precisely locating oneself with a GPS unit, displaying multiple images, that is maps, satellite images, aerial photography, etc., plotting strike and dip symbols, and color coding different physical characteristics of a lithology or contact type, that is unconformity, for example, between the rock strata. Additionally, computers can now perform some tasks that were difficult to accomplish in the field. For example, handwriting or voice recognition and annotating photographs on the spot. Using digital technologies for geological field mapping has many distinct advantages, including number 1, improved precision in the placement of geological features and sample locations using global positioning systems, or what you call as the GPS, and on-screen display of the geospatially corrected imagery and topographic base maps for reference. Number 2 is increased efficiency in drawing field attributed geological lines, because they do not need to be hand transferred or redrawn on another map in the office and then digitized. Number 3 is graphical notation on digital photographs with geological relationships. And finally, assessing key publication in a digital library. Number 9, computer methods for geochemical and petrologic mixing problems. Mixing problems arise frequently in examination of compositional variation in rock bodies, particularly in studies of magmatic differentiation. Previously, the problems were examined graphically, but later geochemists and petrologists were shown the matrix algebra that could be used to obtain least square solutions. Computer programs based on fundamental matrix operations and variations of them have been circulated broadly and used widely by petrologists. The method of Q-mode factor analysis extended for treating compositional data are well suited for all types of chemical and mineralogical mixing problems. The methods can be used not only to estimate the mixing proportions but also to determine the number of n members required in a given problem and to aid in determination of n member composition. And number 10, stratigraphic analysis. Significant progress in the stratigraphic analysis has occurred in several areas of stratigraphy. Multi-band seismic data systems with greater resolution of detail have revolutionized our ability to interpret subsurface stratigraphic units, distributions, lithologies, physical properties, and contained fluids. Now, we are able to predict and map with reasonable accuracy what subsurface stratigraphic sequences will be encountered in poorly explored sedimentary basins. Advances in data interpretation or data representation, mapping methods, and geographic analysis and understanding of trend surfaces have resulted in improved regional stratigraphic analysis and interpretation. Interactive computer technology has permitted the stratigrapher to determine more quickly alternative methods of data display and analysis, which leads to better understanding of relations and more rapid solution of problems. All of these advances have been accompanied by and partially are a result of improved stratigraphic databases and information banks. Computer-based techniques have permeated in the most fields of structural geology. The biggest new thrust has been in the application of finite element methods, which seem destined to play an increasingly important role in structural geology research. Much of the effort in modern information systems has been concentrated in two aspects. The first is in the design and generation of various types of databases. The second is in the design and development of methods to retrieve selectively relevant information from these databases. These activities have had the effect of forcing the geoscientists to re-examine the methods in which earth science data has been collected, recorded, and stored. As a result, some fundamental progress has been made in geoscience information systems apart from the fields of computer and information sciences. The next phase already seems to be in progress. The use of distributed processing techniques, the availability of relatively inexpensive microcomputers, and an emerging communication technology will significantly affect the manner in which geoscientists will gather, store, and assess information. New and improved algorithms for solving geological problems will be developed. Simulation of geological processes and realistic three-dimensional models also will be important in the coming decade. It is possible that a language to express geological concepts and terminology in mathematical terms will be formulated. The next 10 years predictably will give us improved and greater usage of existing quantitative methodologies. Better methods of displaying and depicting stratigraphic data, relationships, and interpretations will arise through greater use of three-dimensional displays, color coding, and improved resolution of output. Better databases will provide broader coverage and permit more comprehensive analysis. Nonetheless, much progress will remain to be accomplished because the final availability of all stratigraphic data in computer data banks seemingly is more distant than one decade. Similarly, data standardization will be greater, but unfortunately probably will not be universal. Better stratigraphic analyses will result from more sophisticated applications of existing techniques to multiple data sets. All of this will become available more readily to geologists by development and marketing of smaller, cheaper, and faster computers having multiple processors and large memories. More field usage of computers by geologists during the next 10 years can be anticipated. Computer workstation-based interpretational software provides the tools to handle mass quantities of data for improved site characterization, In order to improve site investigations, environmental professionals need to consider application of near-surface geophysical and geological methods coupled with the visualization and analysis power of computer workstation-based interpretational systems. Improved understanding of the subsurface geology is an important consideration for development of adequate sampling strategies and the design of workable remediation systems. A variety of Windows-based software applications including word processing, HTML editors, spreadsheets and graphing, image manipulation, drawing, presentation and ArcGIS are mostly used by geologists nowadays. Geologists use computers and software as tools in the areas of geological problem solving, report writing and presentations. Thank you very much.